So, hello, dear students. Good afternoon. Am I audible and visible? Good afternoon. Good afternoon, Shimoga students. Good afternoon, Bhagat. Good afternoon to all of you. So, just let me know in the chat box if I'm visible and audible, or else I'll launch you a poll. Just let me know in the poll if I'm visible and audible. Yes? Am I not audible? Okay. Okay. Great. Okay, fine. So, let me end the poll now. Okay. Fine, students. So, good afternoon to all of you. So we are dealing with the electrochemistry lesson, right? So we have discussed many things in the last two classes of electrochemistry which we have seen. And today, let me recall the previous class, okay, with the two questions. So it would be a recall test for you. So after doing those two questions, we can move on to the new chapters for today, okay? So here for today's recall test, the first question that I have taken is very easy question. What is Faraday's first law of electrolysis? Can you able to see the screen now? Can you able to see the screen? Students, can you able to see the screen now? Yes. Okay. Fine. So can anyone let me know the correct answer for this question in the chat box? What is first Faraday's first law of electrolysis? Just you don't have to give me the definition, just give me the formula alone. So we have studied W is equal to something, right? So what is that something? W is equal to. So Faraday's two laws we have studied. So the first law is W is equal to Z into I into T, right? So the second question is What is the relationship between resistance and resistivity? What is the relationship between resistance and resistivity? Can anyone give me the answer? What is the relationship between resistance and resistivity? Resistance is actually R and resistivity is rho, right? So we have studied one formula for that also. Can anyone give me that formula in the chat box? Can anyone give me the answer for this? Very good. R is equal to rho into L by A. Very good, JNB Shimoga. So R is equal to rho into L by A is the relationship between resistance and resistivity. Okay, so these are some of the things we have discussed in the previous class. And in today's topic, yeah, very good, Srujana. Your answer is correct. So the topics that we are going to cover today are the conductivity cell and batteries and corrosion. Okay. So batteries and corrosion is the last topic of this lesson. So we'll try to complete it by today. And if not, if we couldn't, we can do it in the tomorrow in the next session. Okay. So let me start from the conductivity cell for today. So here I am going to take a cell, conductivity cell, in which we have a tube which is filled with electrolytic solution, and two electrodes are here. One is a platinized anode and the other one is the platinized cathode. And they are connected to battery, ammeter, etc. etc. Okay. Now, conductance is denoted by the letter G. In the last class we have seen, no? Conductance is denoted by the letter G. Conductance and resistance are inversely proportional to each other, or I can say one is the reciprocal of the other. Conductance is the opposite of resistance, right? So G is equal to 1 by R. So this is the relation between conductance and resistance. Okay. And if we substitute the value of R, so we have seen that R is equal to rho into L by A, right? So in place of this R, if you substitute this rho into L by A, you will get a relation for G as L by, I mean 1 by rho into A by L. 1 by rho into A by L. So here you substitute rho into L divided by A, so that A will go to the numerator. So this is what we have achieved. Okay, so this is the next relation. And if you can able to see those two electrodes, anode and cathode, so the distance between the anode electrode and the cathode electrode is actually L. So that is the length between the two electrodes. Okay, and the area of cross section is this, and it is represented by the letter A. So that is what we call here as A and L. Okay. Since conductance is the reciprocal of resistance, conductivity is the reciprocal of resistivity. Okay. So G is actually called as conductance. G is actually called as conductance and R is the resistance. So resistance and conductance are inversely proportional to each other. Likewise, conductivity, which is denoted by the letter kappa. So this conductivity is inversely proportional to resistivity. Resistivity is denoted by the letter rho. Okay, so rho is called as resistivity. Got it? So rho and kappa, these two are inversely proportional to each other, where rho is the conductivity and the SI unit of conductivity is Siemens per meter. Okay, and also I'm going to give you one more relation. L by A is equal to G star, where G star is the cell constant and its unit is meter inverse. Okay, so L by A is called as G star. So here I have A by L. So what I can write here? I can write 1 by G star. I can write this as 1 by G star. And here I have 1 by rho. 1 by rho is actually equal to kappa. So I can write this equation or the relation as G is equal to kappa into 1 by G star. Okay, which is a very important relation you should know. Got it? So instead of 1 by rho, I have substituted kappa, and instead of A by L, I have substituted 1 by G star. Got it? So what are the relations you have to keep in mind? The last formula, and G is equal to 1 by R formula. If A and L are given to you in the question, then you have to go for the second formula also. Is it all right for everyone? So do any of you have any doubt from this conductivity cell? Shall I go for the next slide? Say yes or no. So any doubt from the slide, students? Shall we go for the next? Yes. Thank you so much for your response, Jain Mishimoga. Now we'll go for the classification of substances on the basis of conductivity. Okay. So on the basis of conductivity, the substances are going to get classified into three. The first division is conductor. Okay. And the second division is Nisarga. You want me to explain the previous slide once again? Okay. I'll just go a little bit fast. Try to, yeah. So please try to concentrate. So here from this slide, you are going to learn some formulas. The conductance is the inverse of resistance and conductivity is the inverse of resistivity. Okay. And we have studied R is equal to rho into L by A formula. So in place of this rho, sorry, in place of this R, I have substituted this entire thing and I have got this relation. Okay. Now, since 1 by rho is equal to kappa, instead of this 1 by rho, I have substituted kappa. And here L by A is G star, means A by L is 1 by G star. Okay. So A by L is 1 by G star. So I have substituted 1 by G star and I have got one more relation. Got it? So only the formulas you're going to study from this. G is called as conductance. Is it all right now? Clear? Okay. Okay, fine. Now, as I have said, the substances are classified into three. One is a conductor, and the second is insulator. Third is a semiconductor. Okay. So, how to know whether a particular substance is a conductor or not? By using the kappa value, you can find out. So, what is kappa actually? Conductivity. So, by using the conductivity value, we can able to classify the substance into these three categories. Okay. How? How to find out from the value of kappa? If the kappa value is greater than 10 power 4, then it is called as a conductor of that for that substance. Okay, so examples of some conductors are sodium, copper, silver metal, gold metal. So all these elements will fall under conductors. Okay, next, coming to insulators, if the conductivity value is less than 10 to the power minus 10 Siemens per meter, they are classified into this particular category, which is insulator. Insulator means they don't conduct the electricity, right? Like for example, we can take glass, we can take Teflon. Okay, Teflon means a coating, right? In the non-stick you have a coating, no? So that is a Teflon coating. So these are some of the substances of insulators. Okay, then moving on to semiconductors. So for semiconductors, the kappa value will vary between 10 to the power minus 7 to 10 to the power 4. Okay, minus 7 to 4. So examples are silicon, germanium and copper oxide. Silicon, germanium and copper oxide. So you should know the kappa values and also the examples under each category. Okay. So apart from these three substances, we do have one more also, which is a special case I can say. Okay. So that substance is called as the superconductors. So what is meant by superconductor? Can anyone give me the definition for superconductor? Have you heard of this term superconductor before in any of your lessons in any subject? Has anyone heard of the term superconductors? No? Very good. Very good. Very good. Very good. Shimoga. Students, very good. So, superconductors are the substance. Yeah, substances. Very good, Kaushik. So, which has zero resistivity. Okay? Or infinite conductivity. So, it go on conducts, but it never resists. Okay? Zero resistivity, or you can call it as infinite conductivity also. Got it? So mostly who will fall under this category means metals and alloys at very low temperature. So you know the metals, you know D block metals, you know S block metals, so you know what are metals. And alloys means two or more than two metals combines to form an alloy. Okay, so those are alloys, and metals are the zirconium, zinc, copper, silver, gold. So these are some of the metals. So if they are present at very low temperature, like from 0 to 15 Kelvin, they can act as a superconductor. Okay, so apart from this, some ceramic materials and mixed oxide also show the superconductivity property even at 150 Kelvin also. 150 Kelvin is not very low temperature, but these ceramic material and mixed oxides kind of thing, so you can able to see, right? So these substances can able to act as a superconductor. Okay, so nowadays some researchers are going in this superconductivity topic. Okay, so it is what to say, very important thing we can say for present days. Got it? So what you are going to take from this slide is the three classification of substances and the kappa range for all the three with examples and the definition of superconductor. Clear for all of you? Shall we go for one question from the conductivity topic? Yeah. So here is the question. Kappa is the conductivity of 1 by 50 normal KCl at 298 Kelvin is 0.001765 Siemens per centimeter. And the resistance of the cell containing the solution is 100 ohm. Calculate the cell constant. So what is given in the question? Conductivity is given in the question. Okay, so this is the conductivity. And the resistance is also given to us in the question. So kappa is given, R is given, and we are asked to find out the cell constant, which is G. G is the cell constant. So how to find out this G from resistance and kappa? Any idea? Like which formula has to be applied here to find out the G? Can anyone able to guess which formula has to be applied here to find out G? Just give me the formula alone. We'll proceed. We have temperature, we have the concentration, we have conductivity, we have resistance. So everything we have. We are asked to find out the cell constant. How to find out? G star is equal to K into R. Very good. Very good. G star is equal to K into R. But instead of that R, you can go for conductance. G star is equal to kappa into R. So that can also be taken. Yeah, that can also be taken. Or else you can replace this R resistance is the inverse of conductance. So you can put 1 by G also. So from this formula also you can get it. Yeah, R is equal to 1 by G. G star is equal to K into R. This is the relation which you have set. You can apply directly here also. So G star is equal to kappa into R. Just the direct substitution will give you the answer for this question. Okay. Very good, students. So JNV Shimoga, no, you are doing great today. Very good. So any doubt for anyone? So instead of using all these formulas, you can straight away go for this also. So G star is equal to kappa into R. Okay, is it clear? So we are asked to find out the G star. It is kappa into R. Students, shall we go for the next topic? Let's do the measurement of conductivity now. So how to measure the conductivity? So what is the instrument which we use to find out the conductivity? It is a Wheatstone bridge. Okay, it is a Wheatstone bridge. So I have R1, R2, R3, R4 kind of resistance, and this R2 is actually the conductivity cell and R1 is the variable resistance. It keeps on varying. Okay, and the center you can able to see with the letter P, that is called as the detector. That is called as the detector. So when this detector shows no current, then what happens, for all these four resistors? So R1 by R3 will be equal to R2 by R4. Okay. So this R1 by R3 is equal to R2 by R4. Okay. Now I can rearrange this and can get the value of R2 alone, which is R1 by 3 into 4. So this is the formula to find out the resistance of the conductivity cell when the detector shows no current. Okay, got it? And also we have studied that conductivity kappa is equal to G into G star. Okay, by rearranging you will get this. And instead of writing this G, which is the conductance, we can write it the reciprocal of this conductance, which is actually the resistance. So G is equal to 1 by R. Okay, for R2, it is 1 by R2. So in place of this G, you can substitute 1 by R2 and you can get this relation. Okay, so what are the two relations? R2 is equal to 1 by 3 into 4 and kappa is equal to cell constant divided by the resistance of that conductivity cell. All right, clear for all of you? So this is the instrument. Wheatstone bridge is the instrument which is used to measure the conductivity, okay, of any cell. So now moving forward with this, we are going to learn some important things. The first thing is molar conductivity. So what is molar conductivity? The definition, the formula, everything, the graph which we are going to study under this topic are very important. Okay, so what is molar conductivity? The conductance of the volume V of solution containing 1 mole of electrolyte, 1 mole of electrolyte, 1 mole of electrolyte. So what is an electrolyte? The electrolytic solution which we are going to take in the beaker. Okay, so this is the electrolytic solution which is called as electrolyte. And the concentration should be 1 mole. And the volume of this solution is taken as V. So the conductance of this particular setup, which is kept between two electrodes. So two electrodes are dipped inside this. One is cathode and the other one is anode. And its area of cross section is A. And the distance of unit is, distance is called as length, which is a unit length. Means it will be 1. Okay, distance of unit length. So molar conductivity is actually denoted by the letter lambda m. It is denoted by the letter lambda m. So lambda m is equal to kappa into V. Lambda m is equal to kappa into V, where kappa is the conductivity and V is the volume. Okay. And this volume is going to get rearranged with the one concentration term. And that concentration term is molarity. So what is the formula to find out the molarity of any substance? Can anyone tell me? So we have studied the formula in solutions lesson, right? Can anyone give me the formula of molarity? Do any of you remember the formula? Very good, Kaushik. It is the number of moles of solute divided by Volume of solution in liter. Very good, Srujana. Number of moles of solute divided by volume of solution in liter. Now, if you bring this volume to the other side, you will get N by M, right? So you'll get N by M. So that from that thing only I'm going to substitute here. So V is equal to N by M, okay? And the number of moles is taken as 1 because the molar conductivity definition says, so the concentration is 1 mole. So in place of N, I'm going to substitute 1. Okay, and this is the molarity, this is L. L denotes the liter. So if I want to convert liter to milliliter, then I have to put 1000 there. So V is equal to 1000 divided by M. So in place of V, substitute 1000 by M. If you substitute, you will get this equation for molar conductivity, which is kappa into 1000 by M. A very important formula. Okay. And the unit of molar conductivity is Siemens centimeter square per mole. Got it? So the definition for molar conductivity and the formula for molar conductivity. So these both are very important. So now I'm going to ask you one question. If I dilute the solution, dilution means if I add some more water to the system and if I try to decrease the concentration of the solution, which is actually the dilution, what will happen to the molar conductivity? Will the molar conductivity increases with dilution or it decreases with dilution? What is your answer? Will the molar conductivity increases with dilution or it decreases with dilution? Any idea for anyone? Increases sure. JNV, Ramnagar, Kalaburgi, all of them are going for increases and JNV, Shimoga is going for decreases. So which is correct? What about others? JNV, Kokrajhar also increases. Okay, so majority of you are going for increases and that is the correct answer. Molar conductivity. Yeah. So Kaushik and JNV, Shimoga actually it increases. Okay, molar conductivity increases with dilution. Okay. This is the general term, the common thing. But it will differ somewhat for strong electrolytes and weak electrolytes. So what is meant by strong electrolyte first of all? So it is nothing but the strong acid, the strong base, the strong acid base containing salt. So those are called as strong electrolytes. So strong acid means I can take HCl. Okay. Strong base means I can take sodium hydroxide, NaOH. Strong acid base salt means KCl, NaCl. So all these are the examples of strong electrolytes. So for strong electrolytes, I will get one equation for molar conductivity, which is equal to lambda m naught minus the root of C. C is the concentration here. Okay. Here lambda m naught is the molar conductivity at infinite dilution. Molar conductivity at infinite dilution and C is the concentration. So if I try to draw a graph for strong electrolyte, I will get a line like this. Okay. So I will get a line like this because you can see that this equation is in the format of y is equal to mx plus c. Okay. So where x and y are the axis. So x is nothing but the root of c. So that's why I have written root c in the x-axis and y is actually the lambda m. Okay, it is written in the y-axis and m is the slope here. Slope is negative. So minus 1 is the slope. Okay. So and the c is called as the intercept. Okay, C is called as the intercept. Intercept means the point in which it cuts the y-axis. So this point is called as the intercept, which is lambda m naught. Okay, since the slope is negative, the straight line has to come from top to bottom like this. Okay, so it is a negative slope. It has to come like this. So this is actually a straight line equation. That's why I have got a straight line for this strong electrolyte with my negative slope and lambda m naught as the intercept. Okay. Now, what is the case for weak electrolytes? What is the case for weak electrolytes? So they do follow one law, which is actually called as Oswald dilution law. So we have a big derivation for this Oswald dilution law, but that is not required for our competitive examination. So the last formula which we attain using that Oswald dilution, law of dilution is alpha is directly inversely proportional to root of C. Alpha inversely proportional to this root of C. So this is the final very important relation we will get from this law. Okay, so you just have to keep this in mind. You can ask me, ma'am, what is this alpha? Alpha is the degree of dissociation. Alpha is the degree of dissociation, I can say. And C is the concentration. Both of them are inversely proportional to each other. Okay. So for weak electrolytes, I will not get a straight line like this with the negative slope. So I'll get a curve kind of thing. Okay. So from top to bottom, it goes like this. So this is the curve we get for weak electrolyte. Clear for all of you? So the first thing is molar conductivity definition. And the second is the formula. And the third is for strong electrolyte. And at last for weak electrolyte. For both the things, we have studied one formula each with a gram. So any doubt from this? And you should know that the molar conductivity increases with dilution. Clear? Any doubt, students? Is it clear for all of you? Okay. Now the next second term is equivalent conductivity. So there is only a very small difference between molar conductivity and equivalent conductivity. Okay. So in molar conductivity, we have taken 1 mole of the solution, electrolytic solution, and here the everything is same. Everything is same except that 1 mole. Instead of 1 mole, if you take one equivalent of electrolyte, you take one equivalent of electrolyte, so it will give you the equivalent conductivity. Okay, the conductance of the volume B of solution containing one equivalent of electrolyte kept between two electrodes with area of cross section A and distance of unit length is called as equivalent conductivity. It is denoted by lambda EQ. Okay, so it is equal to kappa into 1000 by N, and the unit is Siemens centimeter square per equivalent. So in the previous case, in the molar conductivity case, we had M here, and in equivalent conductivity, you have to put N. So M is molarity and N is normality. That's all. N is normality. So we also have one relation between molarity and normality. Okay. So normality is equal to molarity into N factor. Molarity into N factor. So instead of this normality, you can write molarity into N factor. If you substitute, you will get a relation like this. Will get a relation like this. And this kappa into 1000 divided by N is equal to something. And can anyone give me that something in the chat box? What is kappa into 1000 by N? Kappa into 1000 by M is equal to what factor or what term or what is the formula? Very good. Very good, Bhagat. It is lambda M. Kappa into 1000 by M is nothing but the molar conductivity, which we have seen. Yeah, good, good. So instead of writing that three terms, kappa into 1000 by M, you can put lambda M in the numerator and divided by N factor, which is there in the formula already. Okay. So this is the relation between equivalent conductivity and molar conductivity. Okay. Is it clear for all of you? So again, from the equivalent conductivity part, you're going to learn the definition and the formula and the last relation which relates both molar and equivalent conductivity. Is it all right for everyone? Shall we go for one question based on this concept? Are you all ready to solve it? Shall we go for the question, students? Yes? Okay. Now moving on to the question. What is the equivalent conductivity of cell containing a 0.1 normal solution of H2SO4 with cell constant 0.5 centimeter inverse and resistance 50 ohm? Also find its molar conductivity. So we are asked to find out both the terms. One is equivalent conductivity and the molar conductivity. And we are provided with the concentration in terms of normality of the solution of H2SO4 and its cell constant is also given. G star is also given and the resistance is also given. So these are the given terms. So from these three given terms, we have to find out lambda, EQ and lambda M. So how to approach? How to approach? Any idea for anyone? How to approach this? Equivalent conductivity is 5,000. Okay, let's see. Okay, now let me go with the solution. So I'm going to start from the conductivity, kappa. So we know that kappa is equal to G star by R. Okay, because G star and R both are given in the question. So I can substitute the values of both the terms and I can get the value of kappa. Okay, so why I have calculated the kappa in the beginning? To substitute in the equivalent conductivity formula. The equivalent conductivity is equal to kappa into 1000 by n, right? So I have this normality value concentration in the question, but I don't have kappa in the question. So that's why I have calculated this kappa using the other given two terms. Okay. Now if you substitute the value of kappa and n, which is 0.01 and 0.1, you will get the equivalent conductivity value as 100 Siemens centimeter square per equivalent. Okay. So now we have got the value or the answer for equivalent conductivity. Now the second question is we have to find out the molar conductivity. So how will you find out? You can use the relationship between both. Molar conductivity is equal to equivalent conductivity into n factor, right? So you can take this formula and substitute the value of equivalent conductivity and n factor and you can straight away get the answer for molar conductivity. Now you may ask me, ma'am, what is n factor over there? N factor is the number of replaceable H plus ions for this H2SO4. Okay, so here is the H2SO4. N factor is the number of replaceable H plus ion. Very good. Very good, Srujana. Yes, very good, Shimoga students. So in H2SO4, I have two H plus, replaceable H plus, right? So N value is equal to 2. So we have got the value for both. We know lambda EQ also and also the value of N. So I can substitute here in the formula and I can get it as 200. Okay. Lambda EQ is 100 and lambda M is 200 Siemens centimeter square per mole. Yeah. So it is easy, right? So do any of you have any doubts from this? I hope it is clear to all of you. If you get any doubt in between or if there is any confusion in solving this question, you can let me know now. Otherwise, you can type yes in the chat box so that I can move on to the next topic. Is everything okay and fine? Clear? Yes? Okay. Okay, good. Now, next we will move on to, yeah. Kohlrausch law. Okay, the very important law. So we have discussed about conductivity cell and we have discussed about the measurement of conductivity. And in the previous case, we have discussed the molar and equivalent conductivity. Okay. Now, the very important thing we are going to discuss, which is Kohlrausch law. Kohlrausch is the name of the scientist. Okay. So, the full name is the Kohlrausch law of independent migration of ions. Independent migration of ions. So, to understand the law and the formulas which we are going to use in this law, I am going to take a container and some cations and anions are present inside the solution. Sodium cation and chloride anion is present inside the container. Okay. So there will be some interaction between two sodium ion and between one sodium and chloride ion. Okay. In this beaker. Now I am going to take another beaker in which I have only two sodium and two chloride. Okay. So in that case, what is going to happen? There will be some force of attraction between with the two sodium and between one sodium and chloride ion. Okay. Now, what is the law? What is the law? The limiting molar conductivity of an electrolyte can be represented as the sum of the individual contribution of the anion and cation. Sum of the individual contributions of the anion and cation is represented as limiting molar conductivity. And this is called as Kohlrausch law. So how to represent this limiting molar conductivity? So we know what is molar conductivity. So it is lambda m. Now what is limiting molar conductivity? If you put 0 in the superscript, it denotes a limiting molar conductivity. Okay. So for any electrolyte, the limiting molar conductivity lambda m naught is represented as sum of the individual contribution of anion and cation. I have Cl minus as anion and sodium plus as cation. If I add these two, it denotes the sum of both. Sum of what actually? Cation anion is there. Sum of what? It is actually the sum of the limiting molar conductivity of both. Okay. So the whole thing is represented by capital lambda. And the for cation separately, if you want to take the molar limiting molar conductivity, you have to use the small lambda. Both are lambda only. This is actually called as capital lambda kind of thing, and this is small lambda we can say. Okay. So both denotes the limiting molar conductivity. Okay, which is the sum of the individual contribution of anion and cation. Now for this NaCl, how to find out the lambda m naught? It is the lambda m naught of Na plus and lambda m naught of Cl minus. That's all. Very simple, very easy. Okay. Clear for all of you? Now how to solve questions from this? So what type of questions can be asked from this Kohlrausch law? So we'll discuss that. Okay. So here is one question. So where lambda m naught for 4 species are given and we are asked to find out the molar conductivities of MgCl2 and KOH at infinite dilution. If you find something like infinite dilution in your question, then you have to think or something has to come in your mind. What is it something? If something is given like infinite dilution, Kohlrausch law should come into your mind. Okay, so it is applicable only for the system at infinite dilution. Okay, now how to find out for MgCl2 and for KOH from the given 4 values? It is very easy actually. So what are the ions present in MgCl2? So in MgCl2, I have magnesium 2 plus and 2 Cl minus. One cation and 2 anions I have. Okay. So if I have to write the lambda m naught for MgCl2, I can write lambda m naught of Mg2 plus. And since I have 2 Cl minus here, 2 into lambda m naught of Cl. I have the values of both Mg2 plus and Cl minus in the question. So I can substitute it directly. Yeah. So for Mg2 plus it is 106, and for Cl minus it is 76.3, and you have to multiply it by 2, and if you do so you will get 258.6 Siemens centimeter square per mole. Very good. Most of you have got the answer for this. So Lakshan is getting 272.6 from JNV Kalaburgi. Are you getting 272? No, you should not get 272. It is 258.6. Okay, very good. So now what about for KOH? Has anyone got the answer for KOH? So in KOH I have K plus and OH minus ion. Very good. Oh, for 272. For 272 you have given for KOH. Okay. Super fast, you're really going super fast. Speed. Okay. So I have to substitute the values of K plus and OH minus, and that will give 272.6 Siemens centimeter square per mole. Great. Very good student. Very good. You people have got it. You guys have grasped the thing so easily. Fine. Now, for a weak electrolyte, like for weak acid, weak base, and weak acid base containing salt, so those are called as weak electrolytes. So for those substances, the molar conductivity depends on degree of dissociation of the electrolyte. Okay, so molar conductivity, which is actually lambda m, it depends on alpha, which is called as degree of dissociation. Okay, so how it is going to depend on each other? Alpha is equal to lambda m by lambda m naught. They are directly proportional to each other. Suppose if I take acetic acid, whose formula is CH3COOH, it has CH3CO minus and H plus. This is actually a weak acid. This is actually a weak acid. This is a weak electrolyte, which is a weak acid. So it is getting dissociated. So that dissociation constant is denoted by Ka. Okay, K is the dissociation constant. A is the acid, dissociation constant of the acid. So that can be denoted as C into alpha square divided by 1 minus alpha. So write these two formulas in your notebook and keep it with you, which is very important. C alpha square by 1 minus alpha, which is Ka, and alpha is equal to lambda m by lambda m naught. All right? Is it okay? Clear for all of you? For weak electrolyte, you have to use these two formulas. Now moving on to the next thing, we'll do one question based on this. If the limiting molar conductivities of barium hydroxide, barium chloride, ammonium chloride are given, calculate the limiting molar conductivity of NH4OH. Can anyone solve this and get me the answer in the chat box? Limiting molar conductivities for 3 species are given. We have to find out the limiting molar conductivity of NH4OH. So how to get NH4OH from these 3 compounds? Any idea? Any idea? So to solve this type of question, what you need to do is try to frame the question first of all. Like how to get this. When barium hydroxide reacts with ammonium chloride, it will form ammonium hydroxide and barium chloride. This is the equation. So this is cation and this is the anion. So they will form one salt, and here hydroxide and NH4 will form another compound. Okay. So we are provided with BaOH twice value, which is 523.28. NH4Cl is 129.8. And it will be, yeah, it is giving NH4OH, which is X. That is what we are going to find out. And for BaCl2, the value is 280. So what you need to do, just equate these two. Equate these two. Very good. So if I equate these two, what I will get? X is equal to, add these two and subtract it with 280. So 523.28 with 129.8. Add these two and what we get? We get 653.8 minus 280. Minus 280, right? So it will be 515, here 3 and 7. Yeah, 373. Very good, very good. So the answer is coming out to be 373. It is actually 373. It is not 251, it is 373. Okay, this is wrong. This is wrong. It is 373. Got it? Very good, very good. Okay, students. This is wrong. Actually, the correct answer should be 373. Okay, 0.08. 0.08. All right. Just give me a second. Okay. Okay, fine. Fine. Now, here is one previous year question from this topic. Previous year question from this particular topic. So, try to solve this and give me the correct answer in the chat box. What could be the correct option? The molar conductance of three compounds are given. The molar conductance of acetic acid at infinite dilution is asked. So how to solve this? Molar conductance at infinite dilution using Kohlrausch law. So apply the Kohlrausch law. So among four compounds, three values are given. You are asked to find out the other one. So try to get the answer, correct answer. You can take 1 minute to solve this. Option C. Are you getting option C? Shimoga is getting option C. Okaraja students are also getting option C. Yes, option C is the correct answer. So how option C is coming out to be the answer for you guys? So you have to use the same method. Okay. So you have to take CH3CO minus, and if this reacts with HCl, it will produce CH3COOH and NaCl. So this is the relation. So for CH3COONA, the value is 91. And for HCl, it is 426.16, which is equal to, this is X, and for NaCl, it is 126.4. So if you rearrange, you will get 390.71 as the correct answer for this question. Okay. So have you all done in this way, or you have used some other methods? So this is one of the very easiest way from which you can get the answer. If you are following some other methods also, no problem, you can use it. Okay. So let me summarize. Let me summarize the formulas we have studied. Cell conductance is equal to 1 by R. Conductance is the reciprocal of resistance, and conductivity is equal to G into G star. Conductivity is G into G star. Pallavi from JNV Shimoga has got this answer. Very good. And molar conductivity is kappa into 1000 by M. Equivalent conductivity is kappa into 1000 by N. And Kohlrausch law is for infinite dilution case, in which the limiting molar conductivity is the sum of individual contribution of anion and cation. And for weak electrolyte, alpha is equal to lambda m by lambda m naught. So these are the very, very important formulas that you need to concentrate from the conductivity cell topic. Is it all right for all of you? So do any of you have any doubts from this? So here we are ending the conductivity cell. The next is batteries and corrosion. So that we will discuss in the next session. So any doubt for anyone from this? Is everything okay and clear for all? Okay. So now, thank you so much for listening to today's lecture. I would like to launch a poll. Just stay in the call. Stay in the call. Just give me a second.